Hey guys, what's going on? So we're going to start the next unit for physics, and it's projectile. And well, we already have done the projectile motion, but now we're going to talk about circular motion. And then eventually we're going to get to angular speed, and then we're going to get to torque as well. We've already done simple harmonic, and we've done projectile motion. So when we talk about projectile and circular motion obviously makes sense. It's circular, right? So if I was driving in a go-kart and I was going at a perfect circle at a constant speed, even though the speed isn't changing, what is the question? The question is, are you accelerating? Are you accelerating because of that? Now remember, acceleration is what? It's a vector, right? Which means there has to be a magnitude and there has to be a direction. So if you're driving in a perfect circle, is your direction changing? 100% it's changing. You could be going, and remember, we've worked with this, with going counterclockwise from the x-axis. So keep that in mind. Yes, you're changing. And because the acceleration is always the rate of velocity, the change of velocity. And remember, velocity again is a vector. And because it's a vector, it has a magnitude and it has a direction. So in this case, yes, your acceleration is going to be changing because your velocity is changing, because even though you're maintaining the same magnitude of speed, you're changing your direction. All right. So velocity is a vector, and a vector that is always tangent to the path of motion. So now we're talking about things that are tangents. So like when you guys get me off onto a tangent talking about different things that you don't want to, because you don't want to do class, you don't want to do class work, and you get me talking about different things that are totally off the subject of what we do, that's what's called a tangent, okay? And these here, up here on this, looking at the circle on the right-hand side of the screen, these are tangents, okay? Because what do we know about motion? Okay, if there's a force that's keeping this going in a circle, but once that force breaks, what's going to happen? This object, say it's spinning around and around and around, say it's a rock at the end of a rope that's spinning, and all of a sudden the force stops, it's going to go off in a straight direction out, and it's going to go in a straight line for wherever that force stops. And we'll talk more about that later. But when we talk about circular motion, okay, we have to, the velocity vector will always be talked about as a tangent to the path of motion, regardless of whatever the shape is. So circular motion at a constant speed, that means the magnitude remains the same, but remember the direction is changing. It's called uniform circular motion. That means it's going all the way through, but it's maintaining. Like, say if this was, say this first tangent is 15 meters per second. If it's uniform circular motion, this is also 15 meters per second, and this is 15 meters per second. Okay? The only thing that changes, what do you notice? This would be moving, kind of northeast. This would be moving kind of northwest, and this would be moving due south. Okay? The only thing that's changing here are the directionals. The directionals are the only things that are changing here. This is not, and this is what tells you that it's uniform circular motion, okay? So just make sure that we understand that the magnitude stays the same, it's just the directional that's changing. Okay, so that's the intro to circular motion. So let's talk about this. So tangential versus centripetal acceleration. So now you're going to go faster and faster. So here's your start spot, okay? Same go-kart. We're driving the same go-kart. Here's your starting spot right here, right? Here's your start spot, and you're starting at 10 meters per second. Well, it's saying that you're going faster and faster. So as you go around, obviously the magnitude will go up. And what do we notice? It goes from 10 to 15. And then from here, from 15 to 18, where it finally finishes. Okay, so again, you have a jump in magnitude. Okay, so again, a positive there. So not only is your magnitude of the number of the velocity changing and going up, but so is your directional. Again, you're going into northeast to ultimately to northwest, and then here southwest. Okay, which actually this would probably be more west southwest. Okay, because you're not going as south as you are as you go west. All right, so what do you notice? So we know that acceleration will equal VF minus VI divided by T. That's what acceleration will be. Okay, actually, I'm sorry, it's not VF, it's VI minus VF. No, I'm right. It's VF minus VI. Sorry, VF minus VI. All right, so we know that that's what it is. So what are we finishing at? Okay, we're finishing at 18 meters per second, right? And then we started at 10 meters per second, okay? And what's the time period? We know, because we're given it here in the problem, that the time period is 4 seconds. Okay, so we have 18 meters per second minus 10 meters per second, which is going to be 8 meters per second divided by 4 seconds, and it equals 2 meters per second squared. So that's what your acceleration is that takes place here. And that is your average tangential acceleration. Tangents, outside. Okay, tangent equals outside. And notice, where do we take these numbers from? We took them from the outside where they were. Okay, tangent means it's outside the circle. When we talk about centripetal, okay, we do that a little bit differently, because when we talk about centripetal acceleration means it's something that's going to be center seeking. Okay, center seeking is what centripetal is. So centripetal acceleration, okay, we know that the definition of acceleration is VF minus VI over T. In this case, when we did it for tangential acceleration, we decided that we were going to use those outside numbers. Okay, but in the end, when we talk about centripetal acceleration is radial in nature. Radial in nature. Well, okay, radial should give you a couple words should pop into your head. Okay, radial. Okay, you should have either radians or radius. Okay, and that's the big part here. Radius is the big part here, because what happens? Because we have to determine it here, what's it going along? This is the center point of the circle. Well, what do we know? Radius always goes from the center point of the circle. All right, we also know that acceleration is the final velocity minus the initial velocity over time. We're not subtracting the vectors, we're not subtracting the speeds, because if we did, these would be the same. So if we did that, your acceleration would be 0. So we have to determine what the theta and what the smaller time period is. What will the triangle yield? Okay, so here you have, when you get to say we go back to the other one, say we go back to the previous circle. So you have this here, we'll just say this is the start here, okay? We're gonna say that's the start, and we're gonna say this is the end piece, okay? You have your starting spot and you have your ending spot. Well, one of these needs to be your initial velocity. Well, this radius right here will match up here. This final velocity will match up with this radius here. All right. So that blue triangle that you see down here. So if you're looking at this, this is V times T right here. Okay. The blue triangle has sides of the radius and the arc of the circle, which is velocity times time. because D equals V times T. All right. The vector triangle, which is the second one here, this is the vector. Okay. And this is the blue triangle. Okay. The vector triangle has the sides of V, V, and then this resultant is going to be VF minus VI. Okay. So the two triangles are similar, and by the geometric proof of the side angle side similarity, we're going to be able to determine that this radius right here, sorry, I was trying to draw and it didn't have the thing up, that this radius will match up here, this radius will match up here, and that VF minus VO will be the resultant there. All right, so that's that. All right, so when we look at centripetal acceleration, okay, because you have similar triangles, and you know that this is V, you know that that's V, it's V over R, which really is VF minus VI over VT. Okay, so by multiplying both sides by velocity, what do we end up getting? We get velocity squared over R. Okay, and then when we look at the unit, and when we look at this unit check, we see, yes, it makes sense because this meter squared will cancel with meters, and you're left with meters per second squared, which should always be the unit for acceleration. All right. So centripetal acceleration vector will always point towards the center of the circle, because remember, centripetal means seeking. Okay? It means center seeking. Right here, AC, what do you notice? Always pointing in. Tangential, always pointing off the outside of the circle. So in this case, the object's moving counterclockwise, right? So the object's moving counterclockwise, but it's speeding up. How do you know that it's speeding up? Well, the velocity is going this way. The acceleration's also going this way. So in this case, it's moving counterclockwise, but this object is speeding up. When we look at this version of it, again, centripetal acceleration pointing into the center of the circle. Velocity is going this way, but the acceleration is going against the velocity. So what do we know? Okay, we know that this object ultimately is slowing down. Why? Because the acceleration is working against velocity. All right? So, centripetal always means center seeking. The magnitude of centripetal acceleration depends both on the velocity and the radius. However, regardless of speed or tangential acceleration, centripetal acceleration will always point towards the center of the circle, which means it is always radial. It's always along the radius. Okay? So keep that in mind. That centripetal acceleration will always point to the center of the circle, and because it's pointing to the center of the circle, it will always be radial in nature. It's along the radius. Okay, so when we talk about resultant acceleration, overall acceleration is the vector sum of the centripetal AC and AT. So total acceleration is A equals AC plus AT. It's true regardless of what way the motion is working. It holds true even when an object is not moving in a perfect circle. The equation above, however, does not include what does it include? It doesn't include velocity. Okay, vectors of different quantities can't be added because remember, acceleration is meters per second squared. Okay, acceleration equals meters per second squared. Velocity is meters per second. You can't add these two together. No, you cannot. Okay, that's why you can't have velocity in the resultant acceleration. Okay, so it doesn't matter. In terms of this, If it's moving if the object's moving counterclockwise, if it's speeding up, if it's slowing down, it does not matter. Okay, you're going to be able to use this equation across the board to be able to do that. But remember, vectors of different units cannot ever be added. All right, we're not going to do non-circular yet, and we're not going to do friction yet. We'll come back to non-circular and friction later. So, force, we know from the very beginning of the year, force equals mass times acceleration, right? Force equals mass times acceleration. But, okay, how do we find out centripetal force? Well, centripetal force is easy. It's going to be mass times centripetal acceleration, which really, when we figure it out, when we know what we know that AC equals V squared over R, if we just substitute this for this, it's going to be, centripetal force is going to be mass times V squared divided by the radius, okay? So FC equals mass times velocity squared over the radius. So if a body is turning, you have to look at all of the forces acting upon it and find that net force. We talked about that when we did free body diagrams, okay? The component of the net force that acts towards the center of the curvature or perpendicular to the body's motion is the centripetal force. Anything pointing in, that's going to be your centripetal force. It's going to be it's going to make almost a right angle. It should make a right angle with anything to it. The component that acts parallel to its motion, either forwards or backwards. So if this was going this way, okay, this is the tangential component of net force. Okay, so this is FA. This is FT, or FC, sorry, not FA, FC. All right, questions? No, clearly there's no questions because none of you are here. All right, so some of the forces that can provide a centripetal force. Friction, 1, keeps the car on the roadway. 2, tension, as in a rock rolling around while attached to a string. So if I was standing in front of you right now, say I had a marker attached to the end of a string, and I was spinning it around and around and around and around, the tension on the string is keeping that marker in motion. Okay, it's also pointing it back into the middle. Normal force, okay, normal force, like in the gravitron we've talked about a little bit at an amusement park, you're up against the wall, it spins, you go up and down, and then the floor drops out. Well, why don't you drop out? Well, that's because the component of normal force on a car on a bank track that acts towards the center, everything's acting towards the center. So normal force, friction, tension, gravity. Why? Gravity pulls us to the what? Central part of the earth. Okay, that's what keeps us on the earth. And the force of gravity between the earth and the sun keeps the earth moving in a nearly circular orbit. And then any other force that is directed towards the center of curvature, such as an applied force, can also be a centripetal force. Okay, we're going to stop there. Today, what I'm going to do is I'm going to post some math assignments for you guys to do, just to get you used to dealing with the formulas. They're going to be simple. We'll walk through them. I will go over them with you as well. And the Easter egg in this video is, how about the Phils taking 2 out of 3 from the defending world champs this weekend? So that's it. Make sure you watch this to the end, and then we'll post the assignment, and we'll go from there. Thanks.